To find the absolute extrema of functions on closed intervals, the extreme value theorem tells us that there must be a maximum and a minimum value for this function. We discussed in class how that could be at either of the endpoints, pi over 3 or 2 pi over 3, or any possible critical points where the first derivative is 0 or undefined on that interval. So first, we need to find the critical points. To do that, we need the first derivative, g prime. The derivative of cosecant is negative cosecant cotangent. And we're interested in where that is 0 or where the derivative is undefined or does not exist. Now I know a whole lot of nothing about the multiplication of cosecant and cotangent and the values of that function. So if I expand it to sine and cosine, maybe I know a little bit more. Cosecant is 1 over sine. And cotangent is cosine over sine. That helps me because this is negative cosine over sine squared. And I care where that function is 0 or where it does not exist on the interval pi over 3 to 2 pi over 3. So let's break this up into two pieces. Where does the top equal to 0? Where does negative cosine x equal 0? And where does sine squared x equals 0, because when the denominator is 0 it won't exist, and when the numerator is 0 we'll get 0. So now we answer those two questions by solving these equations. Cosine of x is 0 when x equals, and you might refer to your circle if you like. There's the unit circle. The cosine value is the x value, so x is 0 not here but here at pi over 2 and here at 3 pi over 2. So that gives me solutions for x here, pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, any multiple that would get me to this angle or to this angle. Now we're only interested, the interval is just pi over 3 to 2 pi over 3. So pi over 3 starts here, well not really there, more like here. And then 2 pi over 3 is not even to pi yet, here. It should be a little more symmetric there. Alright, so that's pi over 3 to 2 pi over 3, so 3 pi over 2 is not on that interval, but pi over 2 is. There's one critical point. Then secondly I asked myself, where does sine squared equal 0? Where that's when sine equals 0, and sine is the y value. So sine is 0 where y is 0 on the circle, which is at 0 or pi. Now neither of those values are on the interval, or 2 pi. So I get to throw them all out and don't have to consider any of them since they're not on the interval. That means we escaped with one critical point at pi over 2. So the second thing we do now is evaluate the original function f of x at the critical points and at the end points. There are two endpoints and we found one critical point. So this is back into the original function, f of the first critical point, pi over 2, and then we'll do the two endpoints, pi over 3 and 2 pi over 3. So pi over 2 is the cosecant of pi over 2, but again, I know a whole lot of nothing about cosecant except that it's 1 over sine, and I know a lot about sine. So sine of pi over 2 is 1. If you refer back to your circle there, that's the y value at pi over 2, so this value of the function 1 over 1 is 1. The cosecant at pi over 3 is 1 over the sine of pi over 3, and at pi over 3 the sine is the square root of 3 over 2. That's the y value. It's a little bit higher than it would have been at pi over 6. So this is 2 over the square roots of 3. And then the cosecant at 2 pi over 3, again, is 1 over the sine of 2 pi over 3. And that y value is the same. They are symmetric. It's a symmetric circle, so 1 over the square root of 3 over 2, or 2 over the square root of 3. Now that we have these values, the third step was to decide who's the biggest and who is the smallest. We need to have, and will have, some absolute max and some absolute min on a closed interval of a continuous function. So which one's smaller? 1 or 2 divided by the square root of 3. Those guys are kind of close. So you could turn 1 into a fraction with the square root of 3 as a denominator. We could say 1 is the square root of 3 over the square root of 3. And then we might want to compare 2 to the square root of 3. Square root of 3 is like 1.17-ish. And 2 is 2. So this guy must be bigger because he has a larger numerator. That means there are 2 absolute maximums. There are 2 values that are exactly the same of this function. So the absolute maximum occurs at 2 pi over 3 and pi over 3. And the values for those absolute maximums are 2 over the square root of 3. You can write them as points. You could tell me that they occur at x equals 2 pi over 3, pi over 3, and the value of the absolute maximum is 2 over the square root of 3, or you can write these coordinate points. The other guy is the minimum, must be, he's the smallest value that came out of the function on these critical points. The absolute minimum is at the point pi over 2, 1. Or the absolute minimum value is 1, and that occurs at x equals pi over 2. So now that we made the decision, we have the solution for this problem by taking cosecant, differentiating, turning him into sine and cosine to not only find where the first derivative is 0 or doesn't exist, but also to evaluate the function.